Hello everybody, I would like to welcome you to this session here, which is related to the training workshop on biogas from organic waste, and this one here in particular, the pre-treatment of substrates. My name is Jan Liebethauer, and you find, in case you want to contact me, my contact data at the very last slide of this presentation. Content of this little workshop here is on pre-treatment of substrate. I would like to start with an introduction and then continue with examples for pre-treatment technologies. Last but not least, if you apply such a pre-treatment technology, you would like to know, of course, if there is an effect, and the actual proof of such effects is not an easy task, and that's why I have added here a few considerations for the assessment of these effects. First of all, when you look at the substrates of anaerobic digestion, you will find a huge variety of different feedstocks. You can have as homogeneous and clean as a maize silage at the top left side here, the picture in a silage pit, high quality substrate for anaerobic digestion. But if you look at the right side, at the right bottom end here, you have organic, separately collected organic fraction of bio-waste. And this usually comes with a lot of impurities, plastic material, stones, whatever you can imagine ends up in such a bin you will find in this substrate. Different than these two solid, rather solid substrates is all liquid fractions, all liquid substrates. Liquid manure, as in the picture above the municipal solid waste here, is one option, but also some industrial processes have a liquid waste stream which can be also treated in anaerobic digestion process. Question is, why would you like to have a pre-treatment process? First of all, pre-treatment comes with the target of increase of gas production, with a better handling of the substrate. These are the two major targets why you would pre-treat a substrate. Increasing gas production follows a disruption of structure in cells. You enlarge the surface of your organic material, and in particular the lignin cellulose compound. This you want to actually destroy to access substrates or components which are encrusted by this lignin cellulose compound. Second, to make this available would also this process of making this fractions available would also lead to an acceleration of the degradation process. You might even increase the biogas potential. I would like to discuss this a little bit later on, more in detail. I think if you achieve acceleration of your available substrate compounds, then you have achieved a lot. I'm not sure if an increase of the biogas potential is actually really possible. Optimization of substrate handling. You make your substrate more homogeneous by pre-treating, by cutting, milling, whatever you're doing it. You avoid substrate separation by doing so. So fibers could swim up, for instance, or heavy particles could sink to the ground if you have a homogeneous substrate with a similar particle size distribution. you avoid such separation tendencies. Of course, technically, it's also important to be able to pump substrates, and sometimes such crushing or milling processes are simply needed to get your substrate streams into the material handling and transportation systems. If you want to know what impact such a pretreatment has on your gas yield, and of course what the relation of costs and energy efficiency in regards to your positive benefits out of your pretreatment technologies is, you need evaluation techniques, methods, and this is not easy to achieve, but I would like to give you some at least guidelines how this can be done. Coming to the next slide, I would like to discuss with you the basic methods of pretreatment processes. There are in general three major lines here. This is the physical methods, which is disintegration based on crushing or milling. Thermal pretreatment, usually by increase of temperature, introduction of steam, and sometimes also pressure, combination of heat and pressure. And last but not least, radiation. This can be either microwave but also ultrasound technologies. Second major group are the chemical methods. You can add, for instance, acids or bases. They are quite effective, but they are not relevant in practice because you have a high demand of acids or bases. You have an impact on the methanogenesis by adding such chemicals, and that's why they are mainly used in laboratory experiments. Last but not least, biological methods. This could be achieved by the addition of microorganisms or simply enzymes. You can add such additives in the process of ensiling your substrates. This can lead to minimization of losses and also kind of have a positive impact on the degradation later on in the digestion process. Or you could add that into your process. However, it's very difficult to really prove the efficiency of such measures because you have a lot of microorganisms already available in the process. They produce usually the enzymes they need for substrate degradation. So adding enzymes to this process might work for very specific substrates, and this has to be considered when aiming at biological methods. There is a huge variety of technologies available on the market. Some of them have been applied only in a few cases, some of them have never left the pilot status, but some of them are usually quite common within the industry. We also have technologies coming over from other application areas. I'm thinking of here maybe sludge treatment in wastewater sludge treatment facilities, or also waste treating, other wastes than biological waste treating units, which also have made their case in the anaerobic digestion process. On the next slide, I would like to show you an overview over different technologies. which are available, and some pictures here. Mechanical processes as the grater or the extrusion process on the left side. Rotor cut is also a cutting, sieve cutting machine. We have other units, as you can see at the on the right side. This is a cross-flow shredder, which has a very sophisticated German name, which you already can see here in this reference. And last but not least, the BioPush ultrasound is an ultrasound unit which has been applied in the sewage sludge applications, but also in the biogas agriculture sector. I have occasionally seen this application. GAMBI process is a heat and pressure unit to actually get access to lignocellulosic materials, which is, I think, in particular when aiming at such more considered sustainable substrate, this is a very interesting application to improve degradation. Now I would like to go a little bit more on the technical details here on these units. You can see here a rotor cut system. It's a sieve and a cutting blade right above the sieve, so the cutting blade shreds the incoming material and forces it through this sieve. And at the very bottom of this vessel here, heavy materials are actually separated out. You can imagine that this separation is also a protection of the cutting unit. This is the problem with all these mechanical units, that as soon as you have a sharp edge required to cut the substrate, the stones or other solid disturbing materials are actually the natural enemy of such sharp edges. So the more sand, the more stones you are forcing through such a system, the faster you get it dull and it won't work anymore. That's why this separation of these stones and other disturbing materials are crucial for a long-term functioning of such cutting pretreatment units. The next one is this cross-flow shredder. As you can see it here, it's a very simple system, as you can see in the picture in the middle of the slide here. It's actually only a chain which is rotating on a very high speed at the bottom of this unit here, and by forcing this chain through the substrate, it destroys whatever comes into this vessel. These units are usually made for any sorts of plastic, or also for devices as refrigerators, things like that. So whenever you have compound materials, they can be destroyed by these units, and this makes this unit also quite insensitive towards disturbing materials. So you can imagine a stone which falls into this here wouldn't hurt this chain a lot. So yeah, it's a lot of energy which is required by these units, but it's quite insensitive towards sand and stones. On the next slide, I would like to introduce quickly the GAMBI process to you. As already said, one of the physical pretreatment technologies is heating it up and pressurizing it. Depending on the temperature, the pressure, and also the duration in the system, you can achieve a certain effect on your substrate. You even can, at very high pressure and very high temperatures, make coal out of the organic substrate. But of course, pressure and temperature also cause costs, and that's why this is always a balance of the effect and the operation costs of such a pretreatment system. So as you can see here, Campi has patented this system, so, and I think the temperature and also the pressure in the system, the retention time in the system, this is also all part of this patent and should be adjusted to the substrate which you are feeding to such a system. Next unit is the ultrasound. Here you have high frequency ultrasound devices sitting outside of the pipe, and the liquids and the organic material which is coming in is actually the sound is applied to this substrate, and the vibrations caused by this ultrasound cause a breakdown of organic material. You can imagine that this helps with conglomerates of microorganisms, but I don't see that large fibers as from straw or even woody material would be affected by such an ultrasound system a lot. So by looking at the principle of these systems, you can already deduce if this would be a good choice for your substrate. So not all of these pretreatment technologies are a very good application to your specific substrate. When looking at advantages and disadvantages of different pretreatment technologies, there's an overview here. This is from an IEA Task 37 publication. You find the reference on the next slide to this. And as already said, you really have to check on your substrate characteristics in order to find the appropriate technology for the pretreatment, which is also in the long term actually very effective to pretreat your substrate. Milling process increases the surface area, makes the substrate easy to handle. It very often also improves the fluidity in the digester. However, it's quite a high energy demand on such a process, and you have maintenance costs, in particular when you have sand and stones in the process. Then these might destroy quickly your sharp edges of the cutting devices. The thermal pretreatment, it increases the enzyme accessibility. However, you have a high heat demand and it's only effective up to a certain temperature. The base addition, something I haven't had an extra slide here, but we had this in the very beginning, so this would be one of the chemical pretreatments. The addition of a base would actually break down lignin. So if you have NaOH, sodium hydroxide, this would be a substance which would break down lignin. However, you need high alkali concentration in the digester to achieve that, or this leads to a high alkali concentration in the digester because you need to add a lot to actually have an effect. And this is high costs on chemicals. Not only this, you also have the chemical at the very end in the digestate and you bring it out to the land. So this is not a good way to go overall. Microbial, I already said, is quite a low energy consumption. If you look only at the introduction at the digester, production of your additive, of course, requires a lot of energy. It has a slow effect and it's very likely not attacking the lignin. Very similar to the enzymatic degradation, again, you simply put the enzymes into the process. This can be a liquid or a powder. However, you need a continuous addition. Costs are not too low, and as already said, I haven't seen a lot of really convincing effects of these enzymes on the process. Steam explosion is a combination of heat and pressure, and then the release of the pressure in a very abrupt way. So you open up the vessel quickly and then you have a high pressure drop. This breaks down lignin and solubilizes a lot of the fractions within the substrate. However, you have heat and electricity demand, and so you really have to check if the effect compensates the costs and the energy demand. Extrusion increases again surface area. It has quite a high energy demand, and here again, extrusion process is also very sensitive to stones. Acids, very similar to bases. It's usually only used within the laboratory applications. Now I would like to discuss the effects of the pretreatment on the gas yield and the gas potential. First of all, why I'm talking about gas potential and gas yield. Gas potential is the maximum of the gas you get out of a substrate. The gas yield is actually the amount of gas you achieve in a technical process. So a technical process has only a defined retention time, it has some limitations in mixing, whatever. So you will never get all the substrate converted in a technical process. That's why the yield is always smaller than the potential. And then the third thing which comes here into the play is the velocity or the rate at which this gas yield can be achieved in a technical process. And a pretreatment has an impact on the rate of the degradation. This is the one thing. And the second, it can have an impact on the potential. As already said, I doubt that there's a lot of impact on the potential, but I think that pretreatment processes can have quite a substantial impact on the degradation rate. In a technical application, an increase of the degradation rate of the substrate would result in an increase of the gas yield because you have a defined retention time, let's say of 20 days. In this defined retention time, you achieve in your standard process 80% of the gas potential. So your yield is 80% of the gas potential. Now you accelerate the degradation rate, and the result of this will be that you get 85–90% of your potential at the same retention time. And this is shown here in this graph. So you can see this red dotted line is an accelerated degradation process, and you end up at the same potential, but in your process, which is T1, this red line here, T1, you can see that you would achieve at this point of operation a higher yield. But it tells us also that if you have a very long retention time, as you can see in T2, then your acceleration of your degradation process has not a large impact on your gas yield. So whenever you want to increase your gas production rate, make sure that your process is actually operated in a way that you have a positive impact on your gas yield. And this can only be achieved by relatively low retention times. Otherwise, the effect of your acceleration is not very pronounced, and you achieve only a little extra of gas. To go a little bit more into detail on that, on the next slide here, you can see the relation of time, and in this case here, retention time in a CSTR, a continuously stirred tank reactor, and the achieved biogas yield given as percent BO. This is percent of the biogas potential. And you can see here two curves, and these two curves represent two substrates with two degradation rates. The blue one, the lower one, is a degradation rate of K equals 0.1, and the black one is a faster degradable substrate with 0.2, K 0.2. K is the conversion rate. If you assume a degradation rate of first order kinetics, then you can see the equation on the right side would look like that. This is the first order kinetic for a CSTR system, and these two curves are actually the depiction of this equation here. And as you can see, at certain retention time, I have been putting down the numbers here for two different points here, 29 days retention time and 71 days retention time. You can see that the difference between these two systems are changing over the course of time. At 29 days retention time, the difference is from 74% to 85%. So it's essentially 11% more gas here. And at 71 days retention time, the difference is only 5.4%, difference between 88 and 93%, 93.4%. So again, what I said on the slide before, if you would change your substrate from the blue curve to the black curve by applying a pretreatment technology, then your impact on your gas yield would be much higher if you have a process which is operating at 29 days retention time compared to a process which is operating at 71-day retention time. So when now transferring this knowledge into an assessment of the effects, you have to do the following steps. So first of all, you have to make a mass balance of the plant, and then you should make an estimation for potential optimization. And this means you have to check on what impact your pretreatment technology would have on your technical material handling operation, then what potential gas yield increase you can expect, And this is important because if you have a very easy degradable substrate and you have a high retention time already, then any pretreatment technology wouldn't help you to increase the gas yield at all. So make sure that you have a sound and reliable estimation on your gas yield increase. Last but not least, energy efficiency. So how much energy you have to put into the pretreatment and what costs are related to that and how this translates or how this is balanced can be compensated by your increase of gas yield. Then I would recommend to really make a test if your gas yield increase, your estimation is actually also showing up in full scale. And these tests are not cheap if they are done well, but think of you spend several $100,000 maybe on a pretreatment technology, then it might be a good idea to invest a few thousand on a test. Then you should make an energy balance, and the question is also what energy form you might have available on site. Let's think of the heat pretreatment. You might have excess heat from the CHP, then this you can easily feed into a pretreatment. But if you need electricity or other expensive energy forms, then of course might be rather expensive operational costs of your pretreatment unit, and you really need to calculate if your extra gas you can expect compensates with these costs. And this is then the fourth step of this evaluation. This is the cost analysis. Make sure that you have all costs, maintenance. I already discussed the blades of a cutting unit, but also maintenance costs on milling units, or also these heat and pressure units. They all have maintenance costs related. The energy costs, and you have to put that in relation to the yield increase and the resulting revenue you can expect from that. Might also be interesting maybe to reduce some maintenance costs, for instance on your existing pumps, which might experience a little bit less wear because you are cutting and removing inerts during the pretreatment process, then other systems might actually like that and have result in less maintenance costs on this side. I always recommend to look at references of the producers and experiences from other sites. You should not only talk to the provider of the technologies. Maybe you find some operators who tell you some experiences, and then based on these investigations, you should make your decision. When you want to check on the effect on the gas yield, there are different test methods. The one is the batch test. This is the standard lab method. It's quite quickly, but problem here is that it not really represents the full-scale continuous operation. So I've seen a lot of experiments where we have seen an impact of a pretreatment technology in the batch test, but once we have transferred that to a continuous test, we haven't seen a yield increase in the continuous test. That's why I would always recommend to do a test really on the technology principle of your system. So if you have a batch test and you have your full-scale plant is operating with a batch system, then this is okay. But if you have a continuously operated system and you want to introduce a pretreatment technology, I highly recommend to go for the test system, which really represents such a full-scale operation. We have on the next slide the determination of the biogas potential, just an example. This is your slide number 17. We have methane yield of untreated and treated store, and you can see that these curves look quite different, and they kind of indicate also a potential change if I assume that the potential is the gas amount produced in the last day. However, this also can be an effect of the test system, so you really have to look with care at such results. When looking at different test methods, you can look at you can compare them by different criteria, which has been done here in this table. This is also part of a publication which is looking at the value of batch tests for biogas potential analysis. And as already said, the batch test is a good laboratory quick evaluation, but however, the transferability of these results to full-scale application, they are limited. Anyhow, pretreatment effects are very difficult to verify. This is also because the precision of all these measurements is not very high. So to really verify a 2, 3, 4, 5% increase of your gas yield by means of such a test is quite difficult. So you would need a lot of replications to obtain a result which is precisely telling you 2 or 3% increase of the gas yield, and much more than 1-digit percentage area. I don't think that this is achievable. So whenever somebody comes to you and says, oh, I have achieved 20% more gas by using a pretreatment, I would be suspicious and would really check on the framework conditions of the test or the framework conditions of the assumptions which have been made to achieve such a very high increase of yield. Here are some numbers on pretreatment technologies, energy input, and as you can see, it's quite different. It really depends on which technology is here analyzed, and of course it makes a difference where you refer the energy input to, if you refer to total solid content or to the cubic meter treated substrate. It's also a huge difference if you have a very liquid substrate or a substrate with a high total solid content. So anyhow, any pretreatment requires energy, and that's why you carefully have to look at the overall effect of such a pretreatment in order to avoid excess energy consumption in the front end, which is not paying off at the back end. When looking at the economic evaluation of these pretreatment technologies, make sure that you consider that operational costs depend on the quantity and of course also on the quality of the substrate. So if you have a lot of disturbing materials in it, you have a lot of fibrous materials, this might cause some headache on your machinery. So really check on the quality of a substrate before looking into operational costs. And in particular, stone, sand, pieces of metal, this can quickly destroy your pretreatment technology if it is sensitive to this. Cutting mills, standard pretreatment is usually something which is has a blade or a cutting device. So, and this is very quickly be destroyed by sand and stones. So maintenance is not only long-term wear, so we have to replace parts, it's also the operational hours per year. So if your unit is very often, if it has a breakdown very often, if it has a standstill very often, so this is costly as well. And this is even more costly because if your front end is not functioning, you cannot feed your digester, and then this stops production and you lose a lot of revenue. Come to the conclusions. The effect of any pretreatment is highly dependent on the characteristics of your substrate, your process, and when I'm saying process, this means if you have a wet fermentation system, dry fermentation system, if you have long retention time, short retention time, and last but not least, of course, the pretreatment technology you select. And any application, any combination of substrate, technology, and pretreatment unit requires a case-by-case study. So there's no standard solution for any process here. And operators of the biogas plants and the provider of the technologies should agree on target values. So if the provider of this unit comes to you, ask for them for this, how they are going to prove the effect on your process and how you can verify that. And yeah, then you might discuss the application of this. There's a broad variety of substrates and disintegration technologies. And that's why there is a substantial need in a really profound and detailed analysis. In my opinion, a disintegration technology is only needed if you have a high fraction of difficult to degrade substrate compounds. So if you have easy degradable substrate as sugar beets, as corn silage, or as food waste, you don't need a pretreatment technology. But if you have straw or lots of lignocellulosic material, woody res in your substrate mix, then you might opt for disintegration technology if your target is an increase of the gas yield. Pretreatment, to sum up, pretreatment is most effective in biogas plants with short retention times and difficult degradable substrates, and this means also that you have high organic loading rates. So for such plants, a pretreatment technology might actually help to increase gas yield. That's it from my side for this substrate pretreatment section. And again, my contact data are here. If you have questions, feel free to contact me.